So before we finalize now on these three gas laws, we need also to understand what are the things we are assuming. So in other words, we can call them assumptions on gas laws, or characteristics of an ideal gas. The assumptions in gas laws, or the properties of an ideal gas, there are three. The things we are assuming for this topic: one, molecules undergo perfectly elastic collisions. The gas molecules we are assuming are undergoing perfectly elastic collisions. Number two, the volume of each molecule is negligible. And then last, number three, the intermolecular force is negligible. In other words, we are assuming it's like the force between each two molecules is almost not there, or is negligible. We are also assuming the particles undergoing perfectly elastic collisions. Then we can look at kinetic theory and gas laws. In other words, how do they relate? How does kinetic theory relate to gas laws? And this is a very, very important component. This is a very, very important component of this topic. Let's start with the Charles. You can see volume is directly proportional to temperature. So how does it take place? The question is how? How does volume increase when you increase the temperature of a gas? So let's say, this for Charles' law. And we are saying, we are considering a balloon full of air. And we are saying volume is directly proportional to temperature. So in other words, what happens when you heat the air? So when you heat the gas, molecules gain kinetic energy and move faster. So when you heat this trapped gas here, because inside here we have gas, when you heat the gas, molecules gain kinetic energy and start moving faster. That is in Brownian motion. And when they move faster, hence increasing rate of bombardment between molecules and between molecules and walls of the container. That's a scientific idea. When you increase the temperature, molecules gain kinetic energy and start moving faster, which increases the rate of collisions between the molecules and also between the molecules and the walls of the container. So, and then hence increasing the volume. So after that, now volume increases. So those are 1, 2, 3, 4 steps, 5 steps. 1, 2, 3, 4, 5. And that is what happens now. That is what happens in Charles' law according to kinetic theory. Remember, kinetic theory of matter states that matter is made up of particles which are in constant random motion. Let's look at number two. Number two, let's look at pressure against temperature. That is pressure law. Pressure law. So we can consider a balloon full of air again, and then we have some gas in the balloon. Then we know pressure is directly proportional to temperature. Pressure is directly proportional to temperature. So that means when you heat the gas, molecules gain kinetic energy. Molecules gain kinetic energy and start moving faster. When you heat the gas, molecules gain kinetic energy and start moving faster. Remember, for this particular case, volume is fixed. So we can say, hence, rate of collisions or bombardment increases. The rate of collisions, the molecules are moving in constant random motion. So that means the rate of collisions is increasing, or the rate of bombardment is increasing. And then what happens? So when the rate of collisions increases, so this one simply means that change in momentum, mv minus mu all over time per unit area. This means that the rate of change in momentum per unit area of the container increases. Remember, we are talking of collisions. When the molecules are bombarding each other and the walls of the container, we are saying the rate of change in momentum, because now they are bombarding at a faster change in momentum. That means they are moving at a higher speed and colliding more. And that means the change in momentum. Remember, this is Newton's second law, whereby we know rate in change in momentum, this is the same as saying force all over area, which simply translates to pressure. So we are saying rate of change in momentum, which according to Newton's second law is force, per unit area increases. Hence, pressure increases. That is when you are heating. These are 1, 2, 3, 4, 5, 6 steps. So we are saying when you heat, molecules gain kinetic energy and move faster. Hence, the rate of collisions or bombardment between molecules and the walls of the container increase, implying that change in momentum per unit, rate of change of momentum per unit area. In other words, force per unit area of the container increases, therefore the pressure inside the container increases. It's important, dear viewer, you understand that these molecules are moving in constant random motion, and that means that when you change the rate of motion, simply it is collisions, because they are moving in constant random motion. Lastly, number 3, let's look at Boyle's law. So for Boyle's, We are still considering the balloon flow of air, but for boils, we know pressure is inversely proportional to volume. We have some gas here. We know pressure is inversely proportional to volume. So what does that mean? When you compress air, when you compress this balloon or the air in this balloon, when you compress this air in the balloon, so what happens? When you compress this air in the balloon, number of molecules per unit area. Number of molecules per unit area of the container increases because you are now bringing the molecules close to each other. And when the molecules increase per unit area, what happens simply is that when the molecules increase per unit area, this implies that so number of molecules per unit area we've said increases. And when it increases, it means number of collisions or the rate. Let's say the rate of bombardment between molecules and between molecules and walls increases. The rate of collisions between molecules and also between molecules and the walls increases, and this simply implies that the next step, rate of change in momentum per unit area, increases. Rate of change in momentum per unit area increases, hence pressure increases. Remember, at this case, temperature is constant. So remember, we must see how pressure is coming in, how it is relating to volume. So we have said when you compress the air, number of molecules per unit area increase. Remember, these molecules are still in constant random motion, and that means when the number increases, the rate of bombardment between the molecules and also between the molecules and the walls of the container increases. And when it increases, rate of change in momentum, according to Newton's second law, the rate of change in momentum is the same as force. Rate of change in momentum per unit area increases, hence pressure increases. So that is how you verify the three laws in terms of kinetic theory of matter. That is how you verify the three laws according to kinetic theory of matter. And this is a very important scientific component of this topic. It's a very important scientific component of this topic which you need to understand because it is very, very essential in physics. So that marks the end of today's session. I wish you all the best.